Hello students, welcome to today's session. In today's session, we will be studying basic of theory of metal cutting. In any manufacturing processes, raw material is converted into desired shape by removing material. This material removing process it can be of two types. It can be chipless or non-chip forming process and second chip forming, that is metal cutting or machining processes. First, chipless or non-chip forming process are those processes in which raw material is shaped under the action of heat, pressure or both. It includes processes like pressing, forging, drawing, casting, spinning, rolling, drop stamping, extrusion and many other processes. Second, that is chip forming or metal cutting or machining processes are those processes in which raw material is shaped into desired dimension by removing excess material in the form of chips by using cutting tool. Here in this diagram, you can clearly see that workpiece is there, tool it is brought in a contact with workpiece and depth of cut is taken and excess material it is removed in a form of chips. The machine on which these operations are carried out, they are called as machine tools. It is includes various operations like cutting, boring, grinding, shearing, and other forms of deformation. Machine tools that are employed, it uses a tools which can be broadly classified as basis on the basis of operation can be broadly classified as single point cutting tool operation, which includes turning, boring, shaping, planing. Second, we have multi-point cutting tool operations in which more number of cutting edges are utilized to remove raw excess material in the form of chips. It includes machines like milling, machines or operations like milling, drilling, tapping, rimming, hobbing, broaching, and sawing. Last type of operations, machine tool operation, it includes abrasive operations in which harder material in the form of fine particles are used to remove excess materials. It includes operations like grinding, lapping, honing, and super finishing process like buffing. The basic elements of chip forming or machining process it includes workpiece, that is raw material, tool which is generally harder, and material it is removed in the form of chips. While carrying out any operations, there are various parameters which affect that operation. It includes first, that is cutting speed. It is nothing but the relative velocity of cutting tool or workpiece. In case of lathe operation, say turning, it is generally considered as largest one. Say the speed of workpiece is higher than speed of cutting tool. That's why in case of lathe operation, cutting speed it is considered as the speed of rotating workpiece. Cutting speed it can be also defined as distance traveled by work surface in a unit time with reference to the cutting edge of tool. Another definition it is as the rate at which cutting edge passes over the surface of workpiece in a unit time. It is normally expressed in a terms unit as meter per minute. Say in a case of turning, cutting speed it is nothing but the speed of rotating workpiece. It is generally given as V is equal to R omega, where R it is nothing but the radius of workpiece and omega it is nothing but 2 pi n upon 16. So finally we get cutting speed for lathe machine as pi dn upon 1000 meter per minute. Second cutting parameter we have it is feed. Feed it is considered for tool. Say it can be defined as a distance advanced by the tool into or along the workpiece each time tool point passes a certain position in its travel over the surface. In case of turning, it is nothing but distance that is moved by tool when workpiece completes one revolution. Feed, it is generally denoted by small f and expressed in a mm per revolution. If feed, it is given in uh, mm per revolution, it can be converted into per minute by multiplying its rpm. Third cutting parameter we have, it is depth of cut. It is nothing but distance through which cutting tool is plunged into workpiece. Thus, in a case of lathe machine, it is nothing but perpendicular distance measured between machine surface and unmachined surface. Say for operation like turning, initial and final diameter is considered. Say D1 is initial diameter and D2 is final diameter. So depth of cut, small d, it is expressed as un unmachined surface, that is D1 diameter, minus machined surface D2 divided by 2 for turning. In order to carry out any operation, cutting tool, it can be cutting cutting tool, it can be arranged into two ways, that is orthogonal cutting and oblique cutting. Orthogonal cutting takes place when cutting edge is straight and perpendicular to the direction of cutting. Say in this diagram, tool, it is moving in this direction parallel to say length, and cutting edge, that is this edge, it is perpendicular to the length of workpiece, that is 90-degree angle is formed between cutting edge and length of raw material. Second, we have oblique cutting. In case of oblique cutting, tool, say cutting edge of tool, it is inclined to the length of workpiece, that is instead of 90-degree angle is formed, instead of 90-degree angle, acute angle or obtuse angle is formed between cutting edge and length of workpiece. Basic difference between orthogonal and oblique cutting, it includes, in case of orthogonal cutting, cutting edge of tool remains normal to the direction of tool feed or workpiece. Say in case of turning operation, this is workpiece rotating say in anti-clockwise direction and tool, it is fed perpendicular to the axis of along the axis of workpiece. So tool remains normal to the direction of feed. Here it is remaining normal to the direction. Whereas in case of oblique cutting, tool remains inclined at acute angle. That is this here acute angle is formed between direction of feed and cutting edge of tool. The direction of chip flow velocity is normal to the direction of cutting edge in a case of orthogonal cutting, whereas in case of oblique cutting, the direction of chip flow velocity is at an angle with normal to the cutting edge of a tool. The angle is known as chip flow angle, that is angle made by chip when it is traveling over the surface of a cutting tool. It is known as chip flow angle. In case of orthogonal cutting, only two forces are acting, that is cutting force and thrust force. So metal may be considered as this method may be considered as a two-dimensional cutting. Whereas in case of oblique cutting, other than cutting force and thrust force, radial forces are also acting. So hence it is considered as a three-dimensional cutting. The example of orthogonal cutting are parting of operation, broaching, swagging, straight milling, and whereas for oblique cutting, it includes lathe turning and drilling. In case of orthogonal cutting, shear force acting, they are small in magnitude, whereas in case of oblique cutting, shear forces that are acting, they are larger in magnitude. Here we have a tool that is maximally used. It is single point cutting tool in case of lathe operation. These are various parts of single point cutting tools. It includes shank, flank, face, nose, base, heel, and cutting edge. One by one, we will see each of this. Shank, it is nothing but main body of a tool, or it is a part of a tool which is gripped in a tool holder. That is this portion of a single point cutting tool. It is held in a tool post. Second, we have a flank. The surface or surfaces below an adjacent cutting edge is called flank. That is, this is cutting edge, suppose. Then face adjacent and below the cutting edge are called flank. That is, this face or this surface, it will be called as a flank, and this one will be also called as a flank, and again this one it will be also called as a flank. So there are two flanks basically, principal flank and face flank. Next, we have face. The top surface of a tool along which chips slides is called face. Say when this cutting edge is brought in a contact with workpiece and chips are removed, chip it will be initially in a contact with this face and it will be flowing over this face. That is rake face. Next, we have a base. It is actually the bearing surface of a tool when it is held in a tool holder or clamp direct in the tool post. That is bottom of a shank. This portion below this, it will be nothing but base. Heel, that is intersection of a flank and the base of a tool. It is curved portion at the bottom of a tool. That is heel. It will be somewhere here below. Cutting edge, it is the edge on the face of a tool which removes material from a workpiece. The total cutting edge consists of side cutting edge, end cutting edge, and base. The lower portion is base, and these are all are cutting edges. Generally, cutting edge or cutting edge they are where say these two cutting edges are meeting. Principal cutting edge and auxiliary cutting edge they are meeting. It is not kept pointed in order to increase tool life. If it is kept pointed, there are more chances of it will break down. So in order to increase tool life, this point it is provided with some radius. That radius it is known as nose radius. The general value of nose radius it is 0.4 mm to 1.6 mm. Next we have terminology of single point cutting tool. There are various angles or say angles included in a nomenclature of single point cutting tool. That is, they are considered while designing any single point cutting tool. That is how these angles they are affecting the tool life and cutting operations. One by one, we will see each of them. In this slide, small introduction is shown. That is, there are rake angle, which includes back rake angle and side rake angle. Second, we have relief or clearance angle. Again, it has two types, end relief angle and side relief angle. Next, that is cutting edge angle. Again, end cutting edge angle and side cutting edge angle. And last, nose radius is there. Here at bottom, you can see three-dimensional diagram or picture of a single point cutting tool, and here they have shown various views: front view, top view, and side view of tool. By observing tool in different view, various angles they can be seen. First, we have a rake angle. That is, in In this diagram, it can be clearly seen that back rake, back rake angle, it is nothing but angled back rake angle. It is angle formed between the face of a tool and a plane parallel to the base. That is face of a tool. This is face of a tool and base parallel, or you can say horizontal line parallel at from the cutting edge. So angle formed between this horizontal line and face of a tool, it is nothing but rake angle. If inclination, again there are two types of rake angle: back rake angle, or it is also called as a top rake angle, and negative rake angle. If inclination is towards shank, it is known as a back rake angle. That is, here you can see inclination is towards the shank, that is going downward. It is called as a back rake angle. When it is measured from the side of a tool, or if you observe the side view of tool, then it is called as a side rake angle. These angles, they mainly affect on a guide of they mainly affect as a guide to chip way from cutting edge, thereby reducing the chip pressure on a face and increasing the neatness of tool so that less power is required for cutting. An increased rake angle, it is called as a positive rake angle, which will reduce if you increase this slope more, it will reduce the strength of cutting edge. Hence, tool used for harder material are given generally smaller rake angle, and those for softer material are given larger rake angle. Generally, in a workshop, when operations they are carried out for mild steel workpiece, rake angle, or say back rake angle, it is positive and it is kept larger. Second, we have negative rake angle. If the face of a tool is so grounded that it slopes upward, or say instead of going downward, it is moving upward towards the flank portion, then rake angle, it is called as a negative rake angle. The, it obviously results in a reduces the neatness of a tool and increases the strength of cutting edge. Such rake is usually employed in the case of carbide tipped tool when they are used for machining extra harder surfaces like hardened steel or for making intermittent cuts. A tool with negative rake angle will have a larger lip angle, resulting in a stronger tool. That is, lip angle here included, it will be larger. Next, positive rake angle, it is recommended under this condition that for machining low strength ferrous and non-ferrous material, positive rake angle can be used. Again, machining at a low speed, it can be we can use positive rake angle. Next, when setup lacks the strength and rigidity, for machining long shaft with smaller diameter, it is desirable to use positive rake angle. And when power uh, low power machine is used, in that case, positive rake angle can be used. Positive rake angle tool can be used. Sorry, negative rake angle, it is recommended when machining high strength alloy. Second, where heavy impact loads are interrupted during machining. Next, for rigid setup when cutting speeds are higher and when carbide tools are used. Generally, carbide tools they are provided with negative rake angle. Back rake angle, it is grounded on a face of a tool. The value of back rake angle, it is generally kept between 8 to 10 degrees. Next, side rake angle, which is observed in a side view. It is grounded on a tool face away from cutting edges. The value of this angle, it is kept maximum up to 14 degree. Next, we have relief or clearance angle. Relief or clearance angle, they are observed in a front view and a side view. That is, re- it is grounded on the end and the side of face of a tool, prevent it from rubbing the workpiece. That is, they are generally grounded. This portion, it is grounded so that direct contact of this face is avoided with workpiece. There are two relief angle, end relief angle and side relief angle. Next we have cutting edge angle. Cutting edge angle, it can be observed in a top view. That is, there are two types of cutting edge angle: side cutting edge angle and end cutting edge angle. That is, angle formed between primary cutting edge and horizontal line in a top view. It is known as side cutting edge angle, and angle formed between auxiliary cutting edge and line perpendicular to the base of a tool is known as end cutting edge angle. Side cutting edge angle, they are also known as lead angle. It is angle between side cutting edge and side of a tool shank. The complementary angle of the side cutting edge angle is called approach angle. The side cutting angle prevents interface of a tool as it enters workpiece when it is initially brought in a contact with the workpiece. The tip of tool is protected at the start of a cut as it enables the tool to contact work first behind the tip. This angle generally varies from 0 to 90 degrees. Larger side cutting edge angle will have more of its length in action for a given depth of a cut, and edge lasts longer. Also, the chip produced will be thinner and wider in case of having large side cutting edge angle, which will distribute the cutting forces and produce over the heat of cutting edge. On other hand, the larger this angle, greater component of force tending to separate the work and tool. Second, we have a cutting edge angle. This angle, it is nothing but angle between end cutting edge, that is auxiliary cutting edge, and line normal to the shank of a tool. It provides clearance or relief to the trailing end of a cutting edge. It thus prevents the rubbing or dragging between machine surface and trailing, that is non-cutting part of a cutting edge. Thus, only small angle may be provided for this purpose. Generally, this value it is kept between 8 degrees to 15 degrees. Next, we have mechanism of chip formation. Here, they have shown shaping operation where workpiece remains stationary and single point cutting tool it is brought in a contact with the workpiece and it moves forward, say towards left direction. Thus, metal when tool is getting in contact with workpiece. Here in this diagram you can see when tool is getting in contact with workpiece, the metal get compressed severely, causing shear stress. This stress is maximum along the plane called shear plane. If ductile, if material of workpiece it is ductile, the metal will flow plastically along shear plane, forming a chip which will flow upward. That is, when tool it is brought in contact with workpiece, the forces that are exerted by tool they are greater than uh, yield strength of material, due to which yield strength and shear strength, due to which material it is deformed due to the forces of tool and it plastically deforms and is removed in a form of a chip. When cutting tool it is forced against the work, the metal layer which is just ahead of the tool is compressed. If tool is forced further, a condition will be reached where stress exceeds ultimate shear strength of given work. This leads the shear along the shear plane and cutting off chip. With further movement of a tool, new layer is compressed and cycle is repeated. The chip formed in metal cutting operation undergoes plastic deformation. It becomes shorter and cross-section area increases. Due to contraction, the length of a chip is shorter than the length of a tool travel along the surface. Here, a microscopic diagram of a chip formation process is shown. That is, deformation of metals along is occurring along shear plane. However, in realistic model that is looking at microscopic level, shear deformation will occur within a shear zone, which includes three shear zones, that is primary shear zone, secondary shear zone, and ternary shear zone. That is primary shear zone, it is along the shear plane of workpiece. Secondary, it is nothing but along the shear plane of tool, and ternary, it is nothing but at the cutting edge where it is getting in a contact with workpiece. Necessary condition for chip formation it should include tool should be harder than work metal. Tool it is properly shaped so that its edges can be effective in a cutting the metal. Third, tool should be enough strong to resist cutting pressure so that it will not fail. And last, movement of tool relative to workpiece or vice versa to make cutting action possible. Due to various cutting parameters, or say when tool it is brought in a contact with workpiece, and cutting parameters like speed, cutting speed and depth of cut and tool condition, the chip form they can be of different types. It includes continuous chips, discontinuous chips that are also called as segmental chips, and continuous chip with built up edges. Here in this diagram you can see that chip when tool it is brought, or say during cutting operation, chip it is continuously flowing in a form of ribbon. Discontinuous chips, it is chips are formed but they are broken after a certain interval. And last, continuous chip with a built up edges, that is small portion of chip get attached to the face or cutting edge of a tool. One by one we will see. Continuous chips they are formed when machining ductile material like low carbon steel, mild steel, copper, aluminum or other material, with cutting tool having larger rake angle and sharp cutting edges. In case of continuous chips, it is flowing continuously like a ribbon. The favorable conditions that are for in order to get continuous chip, it includes high cutting speed, small feed and depth of cut, low friction. Tool used for material will be having low coefficient of friction. In that case, we will get continuous chips. The formation of continuous chips are desirable because smooth surface will be obtained. That is, if chips while carrying out operation, continuous chips are flowing, then quality of surface that will be produced after machining it will be smooth. It will be also helpful in order to increase the tool life and of a tool, and power consumption will be less in case of operation having continuous chips. However, long continuous chips when they are formed, there is a problem of disposal. In order to avoid that problem, chip breakers are provided on a tool. Next, we have discontinuous chips. These types of chips they are produced when machining brittle material like cast iron, bronze with a cutting tool having low rake angle. Whereas for continuous chips, we needed we need to have a rake angle higher. Condition which favors discontinuous chip formation it includes low to medium cutting speed, large feed and depth of cut. That is, depth of cut it is kept larger and feed it is also kept larger, and also the absence of cutting fluid. In case of discontinuous chips, chips are broken into small segments instead of plastic flow along the tool face. The discontinuous chips may also result if material is ductile and coefficient of friction between chip and tool is very high, due to which it will get break and discontinuous chips are obtained. Most of heat generated in the case of discontinuous chips it is carried out by chip itself, and hence tool is heated to a lower temperature, whereas in case of continuous chips tool it is heated to the higher temperature. Next we have continuous chips with view. Continuous chips with view are formed when machining ductile material with cutting tool having smaller rake angle at lower speed. The conditions that gives rise to view are higher value of speed and depth, high friction, lubrication is absent, and high cutting pressure and temperature in a shear zone. This view eventually swept from tool and remain attached to the machine surface. This causes poor surface finish of workpiece which is machined. The presence of built up edges increases the power consumption which is also not desirable. In, in case of continuous chips with view, say uh, chip material in a form of a burr, it gets welded to the cutting edge of a tool. Here in this table we have type of chip when it is formed, type of material that is used, cutting speed, feed and rake angle. So first continuous chips it is formed in a case of ductile material when cutting speed is high, feed it is kept smaller and rake angle also kept smaller. Discontinuous discontinuous chip it will be formed when machining brittle material with low cutting speed, high feed and smaller rake angle. Last, continuous chips with view it is formed when machining ductile material with medium cutting speed, high feed and smaller rake angle. Next, continuous chips as they are providing higher surface finish and quality work. But problem with continuous chip is that it, it get it may cause problem for moving a tool further. So in order to break those chips, we are providing chip breakers. Say in case of carbide tip tools, when they are used for machining, cutting speed it is kept higher due to higher temperature resulting into chip which will be continuous and blue in a color and which will form coil shaped over the face of a tool. Such chips, if they are not broken into part and removed from a surrounding of a metal cutting area, it will affect the machining, which will result in a such a way that tool life it will get reduced by creating carter and rising temperature. Again, it will lead to the poor surface finish of a workpiece, that is chips also they will be coming in a contact with a workpiece. Third, if chips get curdled around rotating workpiece or cutting tool, it may be hazardous to operator. And lastly, very large coil offer a lot of difficulty in their removal. That is, while cleaning process is carried out, they are difficult to remove. So in order to avoid adverse effects, we are providing chip breakers. It is carried out by two ways. That is, first by controlling your tool geometry, and second by obstruction method. Here in this diagram they have shown obstruction method, in which chip breaker it is employed in a case of carbide tool, so that when this chip it will be flowing upward smoothly, it will be broken down by this chip breaker. Second, we have, that is, by controlling tool geometry. It includes groove type, where small groove it is grinded on the face of a tool, so that when, say, when chip it will be flowing, it will be moving along this groove, and it will, after certain, say, rotation, it will break down automatically. Second, we are providing step grinding. Step is grinded on a tool, so that chip will be flowing in this direction, and after reaching it and curling, it will break down automatically. Second rake angle it is provided on a tool through grinding, where together with a small step. And last, clamp type. Here you can see small clamp type, and this is secondary rake angle. I hope up to this it is clear to the student, and in today's lecture we will stop over here.